So last thing we're going to talk about here is systems of equations, which these were embedded really in the first 3 units of the entire year. And so I'm just going to kind of go over a couple different ones and just remind you these are a great review because it's really the same thing you've been doing as you've solved each type of equation. Just now it's going to be given to you a little bit differently. If you remember, a system of equations is when I'm giving you multiple equations, so it could be 2 or more. Here I'm specifically doing 2. This is not going to be 3. These are not the tricky ones from day 1 of this review. What it is when you have a nonlinear specifically. So we're going to have squared terms, we're going to have square roots, things like that, and talk about how we did that. And that's really just a review of everything you've already reviewed in this chapter. So it's going to look something like this. Just remember conceptually, what you are finding for me is where this parabola, since it's a squared term, and this line, since it's only a linear term, intersect. So this can look a lot of different ways. You might have a parabola and a line that goes through it and hits in 2 spots. You could have a parabola and a line that hits it in 1. Or you could have a parabola and a line that never hits it. So you could have 2, 1, or 0 solutions. You won't have more or less than that because you won't have negative. So when we solve these, we're specifically using substitution. What we did way back when is talked about, okay, so if y equals negative 3x squared, we can plug it in for the other y. And I have negative 3x squared equals 6x plus 3. The only thing that's really different between your linear systems and these is that you have to think about all the ways of solving we've talked about. So here, for example, since I have an x squared term, I want to get everything on the same side, and I do want my x squared to be positive, so I'm going to add that 3x squared over. I am going to put it in order so that it's easier to factor. When I look at this then, you're just thinking about all your skills. This I can GCF. And then I can go ahead and factor the insides, multiplying to 1 and adding to 2. It's going to be 1 and 1. When you write out all that factoring, your final answer should be 3 times x plus 1 times x plus 1. Thinking back, this is really from unit 3, sorry. We're going to set each thing equal to 0. The 3 doesn't have a variable, so we don't have to set it equal to 0, but we'll do x plus 1 equals 0, and we get negative 1. The other one, we'd also get negative 1. Once you have that, we now need to find our y value, because remember, this is where our lines are intersecting with our parabola in this case. So we're going to take this negative 1. You can plug it in either spot, whichever one you think will be easier. I'll plug it into the bottom one, because again, it does not matter. 6 times negative 1 plus 3 gives me negative 3 for my y value. So my ordered pair here is negative 1, negative 3. Again, this is the intersection point between the parabola and the line. So this would look something, this one, it's a negative in front of my parabola, so it opens down, and maybe it looks like that. Next chapter, we will talk about actually graphing these, so you can see it here. We're just worried about the algebra. So this is going to be the same kind of idea. You are welcome to go ahead and give this one a try. I will just start talking about it so we can look through it, but it's the same idea. Again, we're going to substitute, so I'm going to plug what I know y equals in for y in the other one. This is again a quadratic, so I want it equal to 0, and I do want my squared term positive, so I'm going to move these 2 to the other side. So I'm going to add x squared, and I'm going to subtract 7. And then what I'm looking at, I want to multiply to 2 and add to 2, which is not going to be possible, so this is not factorable. Now that doesn't immediately mean you have no solution. You do have to think about your quadratic formula like we did back when we talked about Unit 3A again. And so I'm going to go ahead and set up my quadratic formula. B squared minus 4 times A times C all over 2A. It's going to be 4 minus 8, so square root of negative 4, which that should give you kind of a red flag, and we're going to talk about that. I'm going to simplify it because this one's easy to simplify. Square root of negative 4 is 2I. All of these are over 2, so this is really negative 1 plus or minus I. Now when you think about it, we are graphing in this case. I want to know the intersection point between these two equations. On a graph, from what we know, we don't have any eyes on a graph, and so in this scenario, we do in fact have no solution. Now you can't assume that from the fact that I cannot assume that from the fact that we had to use quadratic formula, because you could get an answer that doesn't have an eye. It could just be a decimal intersection point, and that would not be a big deal. But this one, because there's an eye, it is no solution because we cannot graph something and have an intersection point at an imaginary value yet. This last one that I'm going to do deals with your radical equations. When you start this one, you'll notice I have one solve for y and one not solve for y. You are welcome to always solve both of them for y if that makes it easier for you. I know a lot of people prefer that, to maybe just change this around to be 2x minus 6, because then you really are just setting these equal to each other. Whoopsies. And so if that makes more sense to you, you can. Otherwise, you can just plug it into the other equation as it was. When you're solving your radical equations, what is helpful is to isolate your radicand first. So I want to get this by itself. We can move this 2 fairly easily in this case by dividing everything by 2. If it doesn't easily move, you technically don't have to if it's multiplied, as long as you square it correctly, which is the important thing to remember. But this moves easily, and so we can. Then, again, thinking back to Unit 2, to undo that radical, we are going to square both sides. On the left, that's just going to give us x minus 3 because the radical and the square cancel. On the right, I do need to basically imagine writing this twice and FOIL, and you'll get x squared minus 6x plus 9. Now this really does turn into what we just did. It's a quadratic equation, so I'm going to set it equal to 0. Again, I like to keep my x squared positive. I'm going to 7x plus 12. Multiply 12, add to negative 7 is going to be negative 3 and negative 4. Oopsies. It's not an ordered pair, I apologize. X equals 3 and 4. Again, sorry, I kind of jumped there. X minus 3, x minus 4 were my pairs. You set them equal to 0, and you get x is 3 and 4. Now, we do have to go back and check this because we did square our equation. So both of these might not work, and that is kind of a caveat here because you had to check when you solved the equations anyways. You have to check here. 3 and 4 might not both work. So I'm going to check it at the step right before I squared it just to make sure they both work. So 3 minus 3 is 0, square root of 0 is just 0, and the left side is 0. 4 minus 3 is 1, square root of 1 is 1, equals 1. So both of these do check out for x values. Now we do have to get the ordered pairs. To do that again, you can plug it into either equation, whichever you prefer. I'll go ahead and do the second one. When I plug in 3, 2 times 3 minus 6 gives me 0. So my first ordered pair is 3, 0. When I plug in 4, 2 times 4 minus 6, that gives me 2. And so 4, 2 is my other answer. Again, those are your 2 intersection points of this line and the radical function.